Hello guys, today we will discuss about Fermi level in intrinsic semiconductor and its temperature dependence. In last few classes we have discussed about the intrinsic carrier concentration and we have derived the expressions for hole concentration as well as electron concentration, and after that we have derived the expression for intrinsic carrier concentration. Using those things, we will see what is the position of Fermi level in case of an intrinsic semiconductor and how it changes if we are changing the temperature of the semiconductor. So, let us start our discussion on Fermi level. This is the normal energy band diagram for a semiconductor. The valence band and conduction band are separated by a small energy, and that energy is known as forbidden energy gap. We have already derived the expressions for hole concentration in the valence band and electron concentration within the conduction band. Let us see what are those expressions. So, the electron concentration in conduction band is given as n is equals to Nc exponential EF minus Ec by kT, where this Nc is equals to 2 into 2 pi m star kT by h square whole to the power 3 by 2. Here this EF is the Fermi energy, Ec is the bottom of the conduction band, K is Boltzmann constant, T is the absolute temperature, and here this m star is the effective mass of electron, h is Planck's constant. Now, the hole concentration in the valence band is given as P is equals to Nb exponential Eb minus Ef by kT, where Nb is equals to 2 into 2 pi m star kT by h square whole to the power 3 by 2. Here this Ev is the top of the valence band, Ef is again the Fermi level, and K is Boltzmann constant, T is temperature in absolute scale, Mh star is the effective mass of hole, and H is Planck's constants. These derivations we have already discussed in our previous lectures. If you have not gone through those lectures, I recommend please go through those things so that the understanding will be very clear. Now we will consider all these notations in our expressions. This is the bottom of the conduction band represented by Ec, and the energy of the top of the valence band is Ev, and the energy gap between the conduction band and valence band is equals to Eg. In intrinsic semiconductor, the number of electrons, that is N, is equals to the number of holes, that is P, and we have derived the expressions for this N and P. Now substituting the expressions over here, this is the expression for the electron concentration and this is the expression for hole concentration. Here you can see that in this first bracket over here and the first bracket on the right hand side, only this term m star and mh star are different. All other terms are same within these two brackets, that is 2 pi kT by h square. So, apart from this m star and mh star, all will get cancelled from both the sides. This 2 and this 2 will get cancelled from both the sides. Now, what we left with, from here we left only with this m star whole to the power 3 by 2. So, this first term is m star to the power 3 by 2, this exponential Ef minus Ec by kT. On the right hand side we left with mh star whole to the power 3 by 2 and exponential Ev minus Ef by kT. Now we will do some simplifications. Here this m star to the power 3 by 2, it will remain as it is. This exponential term, we are having two terms within this. The first one is exponential Ef by kT and the second term is exponential minus Ec by kT. So, we can divide this exponential term into two terms. One is exponential Ef by kT and the second one is exponential minus EC by KT. Similarly, coming to the right hand side, this mh star whole to the power 3 by 2, that will remain as it is. Here also this exponential term over here, it contains two terms. One is this exponential EV by KT and exponential minus EF by KT. We all know the formula that e to the power a plus b is equals to e to the power a into e to the power b. Here also the same thing I am applying. So this exponential term can be broken into two terms. The first one is exponential EB by KT. This is the first one. Coming to the next one, it is exponential minus EF by KT. So the second term we are getting is exponential minus EF by KT. Now here we will do some reshuffling. First I am taking this mh star to the power 3 by 2 to the right hand side, and I shall combine that term with this mh star whole to the power 3 by 2 on the right hand side. Combining these two, I will get mh star by mh star whole to the power 3 by 2. The second shuffling I have done is this exponential minus EF by KT, which is on the right hand side. I am taking this term to the left hand side and combining with this term, that is exponential EF by KT. This is plus over here, and if I am taking this to the left hand side, it will become, this is negative. After taking this to the left hand side, it will become plus. So I will be getting exponential EF by KT, and this will also exponential EF by KT. So together I will get exponential 2 EF by KT. Coming to the third shuffling, I am taking this exponential minus EC by KT to the right hand side. Again, if I am taking this to the right hand side, this minus sign will go and this will become plus, and that will combine with this term. So combining these two, I will get exponential EV plus EC by KT. So these are the three shuffling I have done, and after doing the reshuffling, the expression what we obtained is equals to exponential 2 EF by KT is equals to mh star by mh star whole to the power 3 by 2 exponential EV plus EC by KT. All the notations I have already told you. So this is the expression we obtained from this upper one after the reshuffling of the terms. Now we will do some further modifications to get the final expression. Then we will see what is the temperature dependence of this Fermi level. So this is the expression we derived in the last slide. Now taking logarithm on both sides, if we take the logarithm of an exponential term, both will cancel, like log e to the power a is equals to a. Similarly, here also if I am taking logarithm of this exponential term, then this logarithm and exponential both will cancel and we will left with this 2 EF by KT. So after taking logarithm for this left hand side term, we get the term as 2 EF by KT. Now coming to the right hand side, we have two terms on the right hand side. The first one is this, if I am taking this, let a, and this is b, logarithm of a into b, that is log a b is equals to, yes, it is log a plus log b. And if it is log a, this total term I have taken a. So log a means, again this is some function, let I take this as x and this 3 by 2 as y. So this will be log x to the power y, and the formula for log x to the power y is y log x. So this term can be written as 3 by 2 log mh star by me star. Now coming to this term, again the logarithm of an exponential term will give us only this term over here. So we will get EV plus EC by KT. So this is log A into log B. So we got log A plus log B, and this one is simplified as 3 by 2 ln ms star by m star, and logarithm of this term is equals to EB plus EC by KT. Our aim is to find out the expression for the Fermi level or Fermi energy EF. So I will take this 2 by KT to the right hand side. Taking this to the right hand side, what we will get? This KT by 2 will get multiplied with both the terms. So KT by 2 into 3 by 2 ln ms star by m star 3 by 2, and here also it is KT by 2 into EV plus EC by KT. In the second term, this KT and KT will get cancelled, and we will get EF is equals to, here it is 3 KT by 2 into 2 is 4. So it is 3 KT by 4 ln mh star by m star whole to the power 3 by 2, and after cancelling this KT, we left with EB plus EC by 2. So the second term is EB plus EC by 2. This is the expression for Fermi level. Now we will see how this Fermi level changes with temperature. First we will consider the absolute zero temperature. If we are considering absolute zero temperature, that means this T is equals to 0. If this T is equals to 0, then the whole term becomes 0. So if this is 0, what is the value of EF? So EF will be EV plus EC by 2. This is 0, so we left with only the second term, and hence we are getting EF is equals to EV plus EC by 2. Now let us understand this position of the Fermi level in the energy band diagram. This is the energy band diagram. This is the valence band, this is conduction band, and EV is the top of the valence band and EC is the bottom of the conduction band, and the expression what we have obtained, that EF is equals to EB plus EC by 2. So this is the mean of these two, that means the Fermi energy lies just between EC and EV. So this is the position of the Fermi level at absolute zero temperature, which is independent of this logarithm term, that is mh star, m star, which are the effective mass of holes and electrons respectively. So at absolute zero temperature, the Fermi level EF is located at the middle of the forbidden gap. This is the forbidden gap, and this EF lies just at the middle of this forbidden energy gap. Now we will see what happens at temperatures other than absolute zero temperature. This is the expression for the Fermi energy. We are considering temperature other than absolute zero temperature. Under this condition, you can see this first term cannot be taken as 0 as we took it in the previous case. This T is not 0 now. Then it depends on this term as well. And here, depending on the relation of mh star and me star, we are having three conditions. First, we will see under the assumption that when the effective mass of electron is equals to the effective mass of hole. Under this condition, what will happen? This will become ln 1. And what is the value of ln 1? That is 0. So if this logarithm value is 0, then this total first term will be equals to 0. Once this first term is equal to 0, then EF is equals to EV plus EC by 2. This is same as the case what we obtained for absolute zero temperature. That means the Fermi energy lies just between EV and EC, just at the middle of these two values. So if this is the conduction band, this is the valence band, this is our top of valence band, that is EV, and this is our bottom of conduction band, that is EC. Then the Fermi level lies just at the middle of these two energy states, that is EC and EV. Thus, the Fermi level EF is located at the middle of the forbidden gap. This is the forbidden gap and Fermi level lies just at the middle. In the previous case, we saw that mh star is equals to m star. Now, suppose this is not equal, then there may be two cases again. This mh star may be greater than m star or mh star may be less than m star. This is what we obtained for the first case when m star is equals to mh star. EF was just at the middle of EC and EV. Now, we will consider the general case when mh star, that is the effective mass of hole, is greater than effective mass of electron. Generally, holes are heavier than electrons. So, this is the most general case when mh star is greater than m star. Under this condition, what will be the value of this logarithm term? This is the numerator is more than the denominator, that means we are getting a term which is more than 1, and we all know that if we are getting a logarithm of a term which is more than 1, that is a positive quantity. If this logarithm term is a positive quantity now, that means with increasing t we are adding more and more positive value to this EV plus EC by 2, which is nothing but the value of the Fermi level at absolute 0 temperature. Now, slowly we are increasing the temperature, and because of that, as this is a positive quantity, we are adding some positive value to this value. This is the value, that EV plus EC by 2. Now, if the temperature is increasing this way, that means as we are increasing the temperature, I am adding some quantity which is more positive with increase in temperature. So, the value of EF will go on increase, that means we will be getting EF like this, is going on increasing. At absolute 0, both are coinciding, but as we are increasing the temperature, we are adding a positive quantity to this value, and the magnitude of that positive quantity goes on increasing with rise in temperature. That is why the separation between these two is increasing as we are increasing the temperature. So, this one is moving more towards the conduction band. This is the reference what we have taken at m star is equals to mh star, but when mh star is more than m star, the Fermi level moves more towards the conduction band with rise in temperature. Thus, Fermi level moves up with rise in temperature. Now, coming to the second case, that is mh star is less than m star. If mh star is less than m star, what happens to this logarithm term? Here this numerator is less than this one. So, we are getting a quantity which is less than 1, and we all know that logarithm of a quantity which is less than 1 is negative. So, this will give us a negative value. Once we are getting a negative value, that means we are subtracting something whose magnitude increases with rise in temperature. That means we will be moving away from this value, and our EF value is decreasing with rise in temperature. For this condition, mh star less than m star, this is the position of the Fermi level with rise in temperature. What happens over here? At absolute 0, again all the three are coinciding over here, but when we are increasing the temperature, we are subtracting a quantity which is increasing with increase in temperature, and hence we are getting the position of the Fermi level moving away from this EF, and it is going more towards the valence band. Thus, For the case when the effective mass of hole is less than the effective mass of electron, the Fermi level moves down with rise in temperature. This is how the Fermi level changes with respect to temperature in case of an intrinsic semiconductor. Let us summarize the thing what we have discussed today. So, at absolute 0, the Fermi level EF is located at the middle of the forbidden gap. If the effective mass of electron and hole are equal, the Fermi level EF is located at the middle of the forbidden gap for all possible temperatures. So, this we have seen through graph and derivation also. Coming to the next one, if the effective mass of hole is greater than that of electron, the Fermi level moves up with rise in temperature. The last case is if the effective mass of hole is smaller than that of electron, the Fermi level moves down with rise in temperature. So, these are the variation of Fermi levels with respect to temperature in case of an intrinsic semiconductor. We will look into the temperature dependence of Fermi levels for extrinsic semiconductor in our next class. Go through all these modules to have a clear understanding. Today we will stop here. Thank you all. Please don't forget to subscribe the channel. If you subscribe it, then you will be getting the notification whenever I will be uploading the next video. Further, if you are finding that the content of these videos are useful for you and for your exams, then you can share the link with your friends, and also you can click on the like button at the bottom. Thank you once again.